In a break, so I don't want the natives to get too restless, but the last panel went a little longer, and so I'm sure that you want to kind of try to get back on schedule. So I'm going to go ahead and start. Let's see, as soon as they have the presentation synced up. Pressing. Is anything happening? Okay. Okay. While they're doing that, let me say that this presentation, yeah, here we are. This presentation was written by myself and my good friend and buddy Dan Adamo. Dan is a retired flight dynamics officer for NASA, supported 60 shuttle flights. Dan and I are kind of emerging as the blues brothers of this space kind of business. The reason for that, I usually play the role of Jake because I tend to be a little short and squatty, and I'm also a little rowdier than Dan is. Dan is the Elwood of the pair. He is tall and thin, and he is definitely the one that is smarter. I've had a lot of fun hanging around Dan because he has taught me a lot. It's, quite frankly, pretty easy to teach me something. In the sense of to make me smarter. Wendell can tell you that it's not very difficult to make me smarter because almost anything that these guys who are really knowledgeable tell me make me smarter. So with that, those of you who have heard me before, I'm pressing, but nothing's happening. Okay. Was I doing something wrong? Okay, he just made me smarter. See? Okay. There. Okay, if you've heard me talk before, you know my second slide is always the same. How many of you are here from NASA? How many NASA people? Okay, I don't know how you got here, but I'm here on my own dime, on my own time, not using government time or government money. So in this venue, even though my day job as it is at NASA, I am not here from the government, but I am here to try to help you. Okay, so keep that in mind. But please be advised, any press in the audience, I am not speaking for the agency or the U.S. government in any way, shape, or form. Whoop. Okay, here's the crux. The crux is we've had 270 missions, over 500 people, over a 100-person years of experience. So the issue is, what are the implications of the evidence that we have learned in the last 50 years of human spaceflight, and how can we apply that to what we do in the next 50 years? Because hopefully it'll be different than what we've done in the last 50 years. I'm really trying on this. Point it here. Press right. Okay, there. All right, there. Those of you who were here last year know this slide that I showed. My whole point here is that in the human dimension, you can do all the sortie missions you want. And as long as they're 2 weeks, a month, maybe 2 months, you can do all those you want, no problem. But as soon as you start doing long duration, and when you go long distances, you have to go longer duration, you have problems. And the biggest problems, of course, are radiation and hypogravity. Once you get to the point where you're talking about settlements and frontiers, and those are venues in which we might have men, women, children, multiple generations, you have got some real showstoppers to deal with. So, we have come up with a kind of a new way to discuss a radiation protection scale. An RP100, which is 100% radiation protection, it's the kind of radiation protection that we're having right here, sitting down, because planet Earth, fortunately, provides a continuous 24/7 passive radiation protection system at the equivalent of 1,030 grams per square centimeter. I want you to remember that number. There are 3 numbers everybody should know. You should know your own cholesterol level, the parts per million of CO2 in the atmosphere, and the radiation protection factor of planet Earth, 1,030 grams per square centimeter. An RP50 is a radiation shield that's basically half of that. And that's what you get at 18,000 feet. Because at 18,000 feet, half the atmosphere is above you, half the atmosphere is below you. RP2 is what the best ISS locations give you. The so-called fallout shelter on ISS. Yeah, right. Radiation protection 2. That's the best ISS does. And if you really want something to be sobering, you can do an RP 0.005. That's the radiation protection equivalent of the spacesuit. 1/2 of 1% of what the Earth gives us 24 hours a day, 7 days a week. So, ladies and gentlemen, I'm sorry to say this to you, but if you still think that astronauts are going to wake up on the surface of the moon and Mars, drink their Tang, have their breakfast, climb into their spacesuit, grab their pick and shovel, and it's out of the airlock for 6 to 8 hours of work on the lunar surface or the Mars surface, I have bad news for you. In my opinion, it ain't gonna happen. And radiation is the reason. It's not because I'm trying to be a spoil sport. All those nice, pretty, shiny aluminum cylinders you see in the PowerPoint presentations on the surface of the moon or Mars, ladies and gentlemen, that is strictly propaganda. Now, you can do that. Technically, you can do that, but the human concept of operations won't permit it. What you might see is this, where you have radiation protection due to putting regolith in sandbags, but actually it would be about 3 times this in terms of scale. You might see this too, but again, you're not going to be seeing a lot of crews in spacesuits on the surface of these. Now, what about Mars? Is Mars any better? No. Mars really has a kind of a whisper of an atmosphere that gives you maybe the equivalent of 16 to 17 grams per square centimeter radiation shielding. That's not very much. So here's the bottom line. If human beings live for prolonged periods on the surface of Mars or the surface of the moon, they'll have to live like ants, earthworms, or moles. It's important that that be the takeaway from this presentation. So, what are the implications? Moon and Mars may never be anything more than sortie destinations, at least with present technology and not without significant new investments in research and enabling technologies. Habitats are going to have to be underground or they're going to have to be shielded. Repeat EVAs by the same crew members will be severely constrained. Why is that? Because you only have a career limit for your exposure to radiation. The current NASA career limits accept a 3% increased incidence of risk of exposure-induced death. What that means is, by the time you finish your NASA career as an astronaut, you have received enough radiation as a result of your space exposure that you now have a 3% increased incidence of not getting cancer, dying from cancer that you got as a result of your exposure. It's the only occupational population on the planet that has accepted a Reed risk. So next time you hear somebody talk about NASA being risk averse, I want you to come back at them with that fact. That means we're going to have robotic precursor missions to scout destinations and prepare the sites for human presence. When the robots do everything, and when the humans arrive, the robots hand the keys to the front door to the astronauts who exit the vehicle and go into the radiation-protected and/or subterranean chamber. Okay? And we're going to have to come up with a gravity prescription. I'm not spending a lot of time on this talk just for time reasons. So here's a quote I came across that I really like. We need to stop this obsessive preoccupation with spherical bodies at the bottom of gravity wells with no atmosphere and no magnetic field. These places just aren't good for us, at least as settlement, frontier, or civilization destinations. Now, of course, the reason I like that quote is because it's my quote. Dan and I were sitting at our favorite academic place, which we call Building C. How many of you have been to Johnson Space Center? Okay, well, you know the buildings are all numbered. There is no Building C. Building C is Chelsea's. Anybody know where Boondoggles is down in Clear Lake City? Okay, well, Chelsea's is just right next door. So when we send emails back and forth, we meet at Chelsea's, and we solve these big space problems. So we were sitting around one day, and we thought, you know, what if We were not constrained by a jobs program, individual contractors. We love contractors, don't get me wrong. You couldn't do space business without contractors. Political considerations like international cooperation. Don't get me wrong, Dan and I both love international cooperation. We're both big proponents of those. Existing hardware or programs of record or space agencies trying to save face. What if you thought about something that did not require a breakthrough in technology like storable cryogens or nuclear propulsions, but it became very clear to us very early that you're going to have heavy lift. I'll talk about that a little later. If you tried to optimize the two most problematic aspects of human space exploration, which are flight dynamics and bioastronautics, what could you do? What could you do? What could you do that was feasible, that used a systems approach, that leveraged the hard lessons of the last 50 years? We decided we wanted to think about doing something bold and innovative, and it had to be beyond Earth orbit. In short, it had to be daring. Well, we Googled and found that, see if we could find any quotes about daring ideas, and we found one. Daring ideas are like chessmen move forward. They may be beaten, but they start a winning game. That's not a recent quote. That's by Goethe. And he said that in the 18th century. So, what's the perfect place, given the hard realities that we have to deal with? Number one, low delta V. Number two, lots of resources. Lots of resources, because the rocket equations mean that you can't rocket up a bunch of resources from Earth. That's not an efficient process. Little or no gravity well, but also at or near normal gravity for people, plants, and animals. Now, that's kind of an oxymoron, isn't it? To have both at the same time, but there are ways to do that, as we will see. Natural radiation protection, permit large redundant ecosystems and a staging area for exploration and expansion. Ladies and gentlemen, those places exist. You're a smart audience. You know where those places are. What are they? Yes. Asteroids. Asteroids. The rest of the talk will be kind of a demonstration of why that is the case. First of all, delta V. Here's some NEO stepping stones to Mars. Notice that it's easier to get to Deimos and Phobos round trip than it is to get to the moon. And here is the reason why the surface of Mars remains a bridge too far today. That won't always be the case, but today it's a bridge too far. Here are some of the accessible NEOs we have with current technology as of March 1st, 2010. And how many of you saw the announcement, I think it was last week, Wendell, you may know better than I, that the new WISE spacecraft had identified 25,000 new asteroids. Now, I don't know how many of those are near-Earth asteroids, Wendell, you may know, but I'll bet there are a bunch. Well, these things are valuable, and despite the comment of one of the people in the last panel, when you look at the value of these, about $20 trillion for a decent-sized asteroid, based on what it's made of. But even if you don't buy this argument, if you look at asteroid 2554 Amun, it's only 2 kilometers in diameter. It's basically an iron-nickel meteorite. It's worth about $20 trillion at current Earth prices. But the cost of rocketing up that amount of material in the asteroid Amun, with current technology, would be $300 quadrillion. That's the cumulative gross global product of Earth for the last 30,000 years. That's a fact. Okay? So these things do have a lot of value. So here's what we're going to have to do. We're going to have to go to the asteroids. We're going to have to burrow in, core out part of the asteroid, process the material, use that material to build our habitats, fairly large-scale habitats that rotate to create gravity. Ladies and gentlemen, there's no air out there, we take our own air. There's no water, we take our own water. There's no food, we take our own food, or we're going to learn how to grow our own food. From a biological standpoint, there's no gravity. We evolved over 3.5 billion years, and there was only one constant. What was that? Gravity. Ladies and gentlemen, we're going to have to take our own gravity with us. And when you look at the biomedical data for the last 50 years, that is very clear, at least to me. So you build your habitat, you rotate the habitat, not the asteroid. You don't have to rotate the asteroid. You don't want to rotate the asteroid. You want to rotate the habitat. And there on the right, there's an asteroid that has an opening that if you had one of those iris doors that you could open and close it, you could put a whole spacecraft in there. Now you have a radiation-protected dry dock. You could even pressurize it if you wanted to. Then you'd have a pressurized, weightless, radiation-protected dry dock. Ladies and gentlemen, that would be the most valuable piece of real estate in the solar system, if you could do that. All right. Now, the problem is that Mars itself is a huge magnet for us, isn't it? It's an emotional magnet. Okay, so regardless of the fact that the surface of the Moon and the surface of Mars may be out, our eyes still can't help but go to Mars, right? So meet Dan and mine's favorite new near-Earth asteroid. What is this? It's not Phobos. Deimos. This is Deimos. Okay? This is Deimos. Deimos has been much maligned. Okay? And that's going to have to stop. If you were on the surface of Deimos, Mars would be 1,000 times bigger than the full moon as seen from the Earth and 400 times brighter. The way to explore Mars is to do it with forward-deployed human beings on Deimos. Here are some of the virtues of Deimos. If you consider Deimos a near-Earth asteroid, a near-Earth object, even though it technically really doesn't meet that definition, it's the third largest when you look at it in asteroids that are from the orbit of Venus to the orbit of Mars. It has a mean diameter of 12.6 kilometers. It has a low delta V, a lower delta V than either the Moon, Phobos, or Eros. And look at this. Escape velocity from Deimos is a whopping 12.5 miles an hour. Now, if you're a flight dynamics person, this is like, I mean, your heart starts to flutter, okay, when you think about the possibilities, because you don't have to go into a gravity well and pull yourself out of a giant gravity well. It's only 20,000 kilometers from the Martian surface. This has utility we'll talk about in just a little bit. It's just above aerosynchronous orbit. Here on Earth, we talk about geosynchronous orbit. On Mars, we talk about aerosynchronous orbit, and Deimos is just above that. And there are some advantages from that, too. There's a launch window every 2.14 years, and that's not the case for a lot of the near-Earth asteroids. A lot of the nearest asteroids, it's a little worse than that, and you can visualize all of Mars from Deimos except extreme polar regions above 82.7 degrees latitude. So if you're above 82.7, can't see it from Deimos. Everything else you can see. Now, since it's only 20,000 kilometers, the round-trip light time from Deimos to Mars and back is a paltry 0.13 seconds. That's 20 times less than the light round-trip time from the Earth to our moon and back. Okay? So you could do a lot of humans-in-the-loop tele-robotic presence from Deimos. That's the way to explore Mars. It's in a locked orbit, so it always, like our moon, it always has the same face that faces Mars as it goes around in its orbit. And it could be a captured carbonaceous chondrite. Man, we'd really be lucky if that were the case, because that means it might actually be moist. There's no evidence of any water on the surface, water of hydration, but in the interior there may be. And it has a low average density, which means that given its size, it's probably either kind of Swiss cheesy on the inside, cavernous, maybe slightly cavernous, or porous. So it might be easy to do that construction that I talked about a little before. And if you look at the NASA Mars Reference Design Architecture, version 5.0, section 3, goals and objective of exploring Mars, you'll find that Deimos, using telepresence, can meet every single one of those goals. Every single one. So Dan and I decided, well, if we wanted to do a human mission to Deimos and back for a crew of 3, what would it entail? And the first thing we did was looked at the duration. We chose a date that is upcoming, that I'll get into in a second. The outbound leg, 240 days. Deimos stay time, 469 days. The return leg, 249 days. If you add a 5% pad, that's 1,000 days. Now, you and I both know that 1,000 days is unacceptable for radiation. So you already know one thing, and that is at your destination, you must implement an RP 100. This will cut the number of your exposed days in half. So when the humans get to Deimos, what's the first thing they need to do? Burrow. Go underground. Okay? So that is a mission requirement. I'm not going to go into this time-wise. We figured out the consumables requirement using the NASA open loop life support, but the open loop life support looks at almost 28 kilograms per person per day. And as a medical person, I know that that's not necessary. So I did I did what I called a Logan modification and brought it down to a manageable number. If you forward deploy your resources that you will need at Deimos and the resources that you'll need coming back from Deimos, you only have to take with you about 9.3 metric tons, which are your outbound consumables and your pad. This is what it would look like. This is an 8-month transit from Earth to Mars. I don't know whether it shows up very well. And you can see the depart date is November 30th, 2011. Now, Dan and I used 2011 because we're not spring chickens anymore. So we wanted to go soon, right? Well, the other reason we chose it is because it's really kind of a worst-case scenario. And we wanted to do that on purpose. Here are some of the innovative architecture elements. So I'm not going to spend a lot of time. I will talk a little later about the Earth parking orbit because we use that as kind of a functional fuel depot. You would incrementally build up your transit vehicle. Now, for radiation protection, you'd need a radical redesign of the human element component of the transfer vehicle, the Mars transfer vehicle. And we'll talk about that in a second. Because what you have to do is you've got to leverage all infrastructure mass, including propellant, as radiation protection. So your transit vehicle has to be built to give you at least RP5. What was the best on space station that we could do? RP2. And the dose rate for interplanetary space is about 2 to 2.5 times what you get at ISS. So your transit vehicle has to be designed to give you RP5. All right? Now, this is the notional view that we all have of an interplanetary spacecraft, right? And this is what we all think of when we think of interplanetary spacecraft. Where does the crew live here? Where are they? Well, they're on the tip of the spear, right? Is that any way to design a vehicle for radiation protection? No, absolutely not. So let me show you the shape of things to come. And that is, if you are going to do an interplanetary vehicle, and you're going to put humans inside, it's going to have to look something like this. Does this look familiar to anybody? What is it? No, it's not the Death Star. No, it's not the Death Star because we won't be sending anything that big. That's right. It's the Discovery vehicle from 2001. Now, even Kubrick and Arthur C. Clarke didn't get it right, did they? Because look at that long stem of hardware. So everything has to be brought up to protect the crew, everything. Now, don't get too taken with how cool all this looks, because really what we're talking about is a functional concept. Probably when we get around to configuring a Mars transport vehicle, it'll look a little more like this. Now, what I was trying to find is a picture of the old Model Ts that the Okies used to get from Oklahoma to California. See, I can do that because I was raised in Oklahoma. So, you know, these are my people, okay? But I couldn't find one on the internet, but I did find this one. Now, look at this thing. Where is the crew? Where are the passengers? On top. If you're designing this for space, where would the crew and the passengers be? In the middle. In the middle, okay? All right, so in the time I have remaining, we're going to talk about assumptions of how you could do a human mission to Deimos with 4 heavy lift launches. Just 4, okay? So let's walk through this. I'm going to do it fast because I'm going to run out of time. The propulsion stages are made up of 15.7% structure. A launch package is limited to 187.7 metric tons inertial mass at LEO. So we are talking about heavy lift, more along the lines of Ares 5. So ladies and gentlemen, let's not let the people in charge talk us into Ares 5 light or direct or some kind of other wimpy heavy lift. We need heavy lift, okay? So if you take anything else out of this, you need heavy lift. All right, you're going to pre and place all return consumables at Deimos. So your first heavy lift launch package, cargo element 1, you send up 1/2 of the hypergolic propulsion stage required for Mars orbit insertion and Deimos rendezvous. The payload mass of that is about 51 metric tons. The IM LEO that you need to do that is 134 metric tons. What's our limit? 187 metric tons. So even on this first launch, we got some positive margin, don't we? All right, the CE2, cargo element 2, is identical to cargo element 1, and that completes the assembly of the Mars orbital insertion stage. CE3 is unique. What you do is you send up something like an inflatable transhab module. We put transhab in quotes because we're not advocating a particular brand. Okay, we're talking about a concept. Plus your open loop crew consumables for 8 months, plus a 5.1% margin. You already saw that in the Logan modified method, that was 9.4 metric tons, plus an additional 23 metric tons for radiation shielding. Even if you encase the crew in all the material that you need to make this Mars transfer vehicle, ladies and gentlemen, even to get a radiation protection level 5, it's still not enough. You'd still have to send up 23 metric tons. Now remember all the debris that they talked about in the last session? I got the answer. That's what you need to do with it. You need to cluster it and use it for your radiation shielding. Now the fourth heavy lift package is the human element. This is a cryogenic trans-Mars injection stage, 46.9 metric tons, plus a CEV to get the crew from the surface of the Earth up to that vehicle. Now, without nuclear propulsion, once you light the fire to leave Earth system, you're committed for a full 1,000 days. There are no Apollo 8-style return aborts. So from that point on, you have to abort to your destination. The total IM LEO that you need to do that, the initial mass at LEO, is 596 metric tons. Current ISS mass is 370 metric tons, but that's not the IM LEO associated with space station assembly. This is a little complicated, but the total IM LEO for the ISS is like 2,500 metric tons. Why is that? Because the space shuttle is such an inefficient system. Okay? When the Russians send up the Russian segment, do they use a shuttle? No, they put it on a Proton. Take it up in one launch. Okay, there's something to be learned from the Russians. Okay, now here's the Earth parking orbit. This is Dan Adamo's concept, and I think it's brilliant. You don't put things up in a low Earth orbit. You put it in an Earth departure orbit or an Earth parking orbit. This orbit, first of all, in order to even get into this orbit, you got to do a burn of almost 3 kilometers per second to put yourself in this orbit. This is basically a 2-day giant orbit that almost gets you out of the Earth-Moon system. And you do that with your cryogenic stage, because each one of these lifts has an Earth departure stage that has cryogens. So you use it right then. Put your hardware in this Earth departure orbit. When you send up the fourth mission, the human element orbits the Earth one time and then goes into a rendezvous burn, again, of about 3 kilometers per second, and a day later, rendezvous with the rest of the cargo. Okay, then another day later, you come back, and if you need the time to check out your systems, you go once more, and then once you come back here, what do you do with that CEV that you use getting up from Earth? You de-dock it. You don't need it. It's dead weight then. You don't want to take that to Mars with you, because you've already pre-deployed the return vehicle that you're going to use to come home. So why take that all the way to Mars? So you take that out, you do your trans-Mars ignition burn, which is only a little more than 1 kilometer a second. And then you're on your way to Mars, okay? In 240 days, you're there in Mars space. I'm not going to that. Time doesn't permit me. So here's rendezvousing with Mars. We're looking down on the North Pole of Mars. You come by, and on the backside of Mars, you do a burn of 1.637 kilometers per second, then another burn of 680 meters per second, And basically that's a Holman transfer that puts you right to the point that Deimos is when you get there. Okay, can you guys then do the movie? And then as soon as I do the movie, I'm kind of done. Now, Dan Adamo put together an amazingly high-fidelity version of the rendezvous at Mars and also at Deimos, and it's real spectacular. So I hope this works. I'm going to try to narrate it as it happens. He did this with Celestia, okay, and this is very high fidelity. So go ahead and start the movie. So here we are. I can't read this, but we're probably going very, very fast, you know, compressing time. So you're about ready to see Mars get much bigger. And this is the only thing we could use to look at the spacecraft, even though that's not what it would look like. So here you are. You come into Mars, and you go around the backside of Mars. You do your burn. For about an hour, you don't have the sun, and for about another hour, you can't communicate with the Earth. You come back around the back of Mars. There's Earth right there. I can't see that very well. This screen's a little better, I think. It's not? Okay. Maybe somebody can turn off the overheads a little bit. But at any rate, there's Deimos. So you're coming in on Deimos. You're about 1,200 times time compressed. And now you're dropping down to 100 times real time. And there's Deimos. Deimos gets bigger and bigger and bigger. And finally, you're about 10 times real time. You do your burn. And you come to a full stop right above the terminator of Deimos. And this is what it would look like. And when the craft flew around Mars, those of you who know your Mars topography could see the actual topography that you would see. Okay, now we're going to back off from Deimos here in just a second. And we're going to stop. We're going to fix our position relative to the stars, and we're just going to follow Deimos in an orbit around Mars. That's what it would look like. Okay? Goes all the way around. And then what we're going to do, once we do one revolution, there's Mars, comes around, there's Phobos. Now what we're going to do is, instead of being the inertial reference to the stars, now we're going to turn and face Mars. And basically do a fly around Deimos, but be looking toward Mars. Okay, so there we go. There's Phobos right. Now look, see how slow Mars turns? If you want to do telerobotics to an asset on Mars, from Deimos you can follow it for almost 2.5 Martian days. And that's what makes Deimos far superior to Phobos. Phobos rises and sets 4 times a day. It would be like the old shuttle AOS, LOS system before we had TDRS. And you can see that the sun, it's only in the equinox that Mars would block out the sun if you were at Deimos. And I think that's probably the end. So let's go back to the slide presentation. Let me do my last slide. So I kind of started with a quote, and so I want to end with a quote. And that's this quote: "All men dream, but not equally. Those who dream by night in the dusty recesses of their minds wake up in the day to find it was vanity. But the dreamers of the day are dangerous men, for they may act on their dreams with open eyes to make them possible." So I hope I've infected you with this idea of a mission to Deimos. And I know we're getting ready to go on the break. If you want to ask questions, that's fine, but I think let's release everybody else, because I don't want you to start, even though I'm one of the Blues Brothers, I don't want to have to erect my chicken wire by keeping you here late. Okay? Thank you.
Guess they turned that one off. All right, he's right. We are going to go on a networking break right now, and we'll come back and do the International Space Station Open for Business panel. Thanks. Yeah, 15 minutes, sorry.
60 shuttle flights. Dan and I are kind of emerging as the Blues Brothers of this space kind of business. The reason for that, I usually play the role of Jake, because I tend to be a little short and squatty, and I'm also a little rowdier than Dan is. Dan is the Elwood of the pair. He is tall and thin, and he is definitely the one that is smarter. I've had a lot of fun hanging around Dan because he has taught me a lot. It's, quite frankly, pretty easy to teach me something in the sense of to make me smarter. Wendell can tell you that it's not very difficult to make me smarter, because almost anything that these guys who are really knowledgeable tell me make me smarter. So with that, those of you who have heard me before, I'm pressing, but nothing's happening. Okay. Was I doing something wrong?
No, it's just how I got it.
Okay, he just made me smarter. See? Okay. There. Okay, if you've heard me talk before, you know my second slide is always the same. How many of you are here from NASA? How many NASA people? Okay, I don't know how you got here, but I'm here on my own dime, on my own time, not using government time or government money. So in this venue, even though my day job is at NASA, I am not here from the government, but I am here to try to help you. Okay, so keep that in mind. But please be advised, any press in the audience, I am not speaking for the agency or the U.S. government in any way, shape, or form. Whoop. Okay, here's the crux. The crux is we've had 270 missions, over 500 people, over a 100-person years of experience. So the issue is, what are the implications of the evidence that we have learned in the last 50 years of human spaceflight, and how can we apply that to what we do in the next 50 years? Because hopefully it'll be different than what we've done in the last 50 years. I'm really trying on this. Point it here. Press right. Okay, there. All right, there. Those of you who were here last year know this slide that I showed. My whole point here, you in a break, so I don't want the natives to get too restless, but the last panel went a little longer, and so I'm sure that you want to kind of try to get back on schedule. So I'm going to go ahead and start. Let's see, as soon as they have the presentation synced up. I'm pressing. Is anything happening? Okay. Okay. While they're doing that, let me say that this presentation, yeah, here we are. This presentation was written by myself and my good friend and buddy, Dan Adamo. Dan is a retired flight dynamics officer for NASA, supported is that in the human dimension, you can do all the sortie missions you want. And as long as they're 2 weeks, a month, maybe 2 months, you can do all those you want, no problem. But as soon as you start doing long duration, and when you go long distances, you have to go longer duration, you have problems. And the biggest problems, of course, are radiation and hypogravity. Once you get to the point where you're talking about settlements and frontiers, and those are venues in which we might have men, women, children, multiple generations, you have got some real showstoppers to deal with. So, we have come up with a kind of a new way to discuss a radiation protection scale. An RP100, which is 100% radiation protection, it's the kind of radiation protection that we're having right here, sitting down, because planet Earth, fortunately, provides a